Lecture 8. In this concluding lecture on forced harmonic motion, we will investigate the resonance phenomenon. So as we saw in the previous lecture, for systems that can be described by this kind of differential equation, where there's an external harmonic force with force amplitude f0 and being applied at an angular frequency of omega f, then we can find a steady state solution which describes the, in quotation marks, the long-term behavior of the system. Long-term, how long is depends on the parameters. We saw in exercise 1 in the previous lecture, it's basically just a second, and the full solution is indistinguishable from the steady state one. But either way, long-term, in quotation marks long, will be described by this formula. Which we can also write in this form by taking out m as a common factor in the bottom square root. And then this term has some interesting consequences. Now, what we want to do now is see what the amplitude, how the amplitude changes if the frequency of the external force is modified. So clearly, how severe or how large the amplitude of the oscillations of the steady state is depends on what the frequency or what the angular frequency of that external force is, because the omega f terms appears in the amplitude. So what we know is there will be, in the long term, there will be oscillations. The steady state says there will be oscillations given by this term, and the oscillations will be the same frequency as that of the external force, which makes sense, I suppose, when you think about it. And the amplitude of those oscillations will be given by this green term. And it clearly depends on what the applied frequency or what the frequency of the external force is. So let's see what happens if we plot that green term versus different values of the angular frequency of the harmonic force. So we'll start here at when the external force is being applied at 2 radians per second, right up to where it's being applied at 18 radians per second. And for each of these values, we'll work out, plot what is the amplitude of the resulting oscillations. And we'll do this for several different b values. Okay, and there you see very nicely indicated the resonance phenomenon. As the angular frequency of the external force approaches that of the natural frequency of the system, look at the parameters here are exactly the same as in that exercise 1. So what is the natural frequency here? What is the frequency of the associated simple harmonic motion? Remember, that is omega equal to the square root of k over m. That is 2500 divided by 25 is 100. So square root of that is 10. So the angular frequency for this system is 10 radians per second. And as the angular frequency of the external force approaches it, you get this resonant effect. The amplitudes of the oscillations shoot up very dramatically, if the damping isn't too bad. If the damping is too large, then there's not much of an effect. If it is very large, then there's no noticeable effect. And the reason for this is very similar to pushing someone on a swing. Person is just swinging on a swing. You're standing on the bottom. As they reach the bottom, you give them another little push, and then they go a little bit higher. That's effectively the analog of what the mathematics is doing here. The system oscillates by itself, but we're applying a force in a frequency that's the same as the frequency which it is oscillating. So just like a person pushing someone on a swing, as they get to the bottom, this force here is doing the same, and each time giving a little bit more energy. And if it does that at a proper frequency, that it ends up to be a lot of extra energy, and you get to much higher, even 25 meters, according to this, in this case. The red case, though, just shoots up. So that is when there's no damping. So let's see, perhaps we just missed the peak. Perhaps the peak is a little bit higher up. So how about if we make this 250? Let's see. Let's make it 250 and do the same again. Not much difference. Okay, and the reason that we see that is because there is no peak. And to understand, I have to understand why blue has got a peak at all. So what happens in this blue curve, when the damping force is 50 newtons per meter per second, the external force is applying at the right frequency so that it gives a little bit of extra push and get a little bit more extra energy until the object moves faster and faster and faster and faster each time. But it can only go so fast because there is a damping force present. And what does the damping force in the blue case mean? It means 50 newtons for every meter per second. So it means that the velocity that you gain with the resonant effect can't just go up indefinitely. At some point, the damping force will simply be too large. You can't get to 1,000 meters per second because that would mean you'd have a 50,000 Newton damping force. So yes, you're going to get faster. The mass will move faster and faster and faster, but only so fast. Eventually, the damping force will override the contribution of the external harmonic force. But in the red case, with the red graph, is a case where there is no damping force. So there's nothing stopping the energy from accumulating. And it just shoots up to infinity. So it doesn't have a bound. So the red case is, in other words, not a realistic case. So you can't have that. The only cases that are realistic are the ones where there's at least some measure of damping. And the less the damping is, the more severe the resonance effect will be. Okay, but as you'll notice, which is a little bit less clear on this graph, so let's go back to the previous one. Where does that peak occur? 10 radians per second is the natural frequency, but it doesn't appear as if this peak, the resonant effect, is exactly on it. It's close to it. This blue one is very close to it, but the green one isn't. It's a little bit here towards the left. And that becomes clear if you look at the expression itself, or you start to get an idea why. This term, if omega f, so what we just saw is if omega f approaches omega, then this amplitude term becomes very large. But when this term is clearly a minimum when omega f is the same as omega, then it is 0. For omega f anything other than omega, then this is just ever increasing value. So this value that becomes smallest when omega f is equal to omega. However, the entire expression is not at the minimum when omega f is equal to omega because of this term. It is slightly off of omega. However, if you calculate the velocity and you consider the velocity amplitude instead, so now the velocity amplitude is given by this expression, then you can simplify it. So I take the omega f down below, so I write it here. I write the omega f from down up there as 1 over omega f to the left of the square root, and then I take it in, and then I've got this expression. And this expression and this entire expression will be at the minimum when omega f is equal to omega. So the velocity amplitude, if we investigate the resonance for it, should be exactly at omega, not close to it. So we can see that very clearly if we plot the graphs. So this is now for the velocity amplitude, not the displacement amplitude. And you see there the resonance effect is precisely at the natural frequency of 10 radians per second. Now, when it comes to questions and problems, and we've got to answer questions about resonance, we will consider the resonance effect to be greatest when omega f, the angular frequency of the external force, is equal to the natural frequency omega. So for us, resonance will mean omega equal to omega f, though we just have to bear in mind that it is technically a little bit more complicated than that. If you're talking about the velocity amplitude for the kind of systems that we've modeled, then yes, the resonance is greatest when omega f is equal to omega. But for displacement amplitude, at least it's going to be slightly less. The greatest resonance will be slightly or a little bit less than the natural frequency. But okay, let's move on to some problems. Okay, so exercise 2. We have a system where we are given the mass and the spring constant. There's a spring with a spring constant and a damping force, which is given 0.50 kilograms per second, and it's been driven by a harmonically varying force of a certain amplitude. And then we've got to find the amplitude and phase constant of the steady state motion when the angular velocity is one of two values. Okay, good. Okay, so what we've got to do is take the steady state motion. So let's say that's given by x of t. So let's say x of t is the steady state motion. So we know that, we've seen that that is going to be equal to a cos omega f t minus theta. It's that particular solution. That is all that's left if the system is left long enough. The other part, the complementary part, which we call also the transient part for transient solution in this kind of these kind of problems, because it simply dies out, and then this is all that's left if a is of this form, and that f0 over that enormous term. Okay, omega f b squared was the first term, plus then k minus m omega f squared. Good. And tan of theta must be equal to omega f b over m. Let's use this formula. Omega squared minus omega f squared. Good. And for easy reference, let's just write down what we have. The mass is 10 grams. Spring constant 36 Newton per meter. Damping constant 0.50 kilogram per second. And if you wonder where that comes from, we defined the damping constant as newtons per meter per second, which makes sense. For every meter per second, there's that many newtons of force. In other words, newton seconds per meter. But the newton is 1 kilogram meter per second. Sorry, other way around. Newton meter per Newton per meter per second. No, that's okay. No, that's okay. Okay, so Newton is 1 kilogram meter per second squared. So over that second per meter, so second, meter, kilograms per second. Okay, so this is sometimes also used for the damping constant. What else are we given? The force amplitude of that external harmonic force, 3.6 newtons. Its frequency, well, that is different for part A and part B. We're going to use omega, so let's see what that is. K over m. 36 divided by 1 over 100 is 3,600. And square root of 3,600 is just 60. And the units of this, of course, is radians per second. Okay. And for part A, we've got to consider the case where omega f is 8.0 radians per second, and for part B, where omega f is 80 radians per second, and find A and theta in both cases. So it's simple as that. So kind of a boring question. So okay, let's see. So now I just have to pay attention to what we're doing. Okay, so that, all right. 3.6 divided by square root of, what's that? Omega f is 8 here, 8 times b, so that's 4. So 4 squared, okay. Plus, what's that? K 36 minus 0.01 times omega f squared, so that's 64. Okay, so just 0.64. Okay, good. So all right, that's it. So in centimeters. That's what we can tell about that. Okay, and let's calculate the A here as well, because we have the formula in the calculator. So okay, what's going to change? So first off, this was m omega. Now omega f is 80 squared, so that is 6,400 times 100th. So it will become 64. This term is now 80 times 0.5, so that becomes 40. Okay. Okay, so this one is 7.4 centimeters. Okay, good. Okay, now we go to theta. Now you just have to remember, if you want to use tan inverse on this, then we just have to check that it's positive. If it's negative, then, and we're using this formula, then we've got to add pi to it. Okay. So tan inverse. And we also know that happens when omega is less than omega f, which is not the case here, but it is the case here. So here we expect theta to work out negative, but not here. Okay. Okay, so let's say that whole story. 8 times 0.5 is 4 divided by, so this is 400 is the first one. Let's just check. 8 times 0.5 is 4 divided by 400 divided by, okay, what do we have here? Omega squared, that's going to be 3,600 minus 64 in this case. Okay. Okay, 0.11. So, well, radians, in other words. Okay. In this case, now we've got mass 80. So what else changes? Now omega f just becomes 80 from 8. So this should just be 4,000 then. Because, yeah, so 80, so the 40, and then, yeah, that's fine. And then this one will become minus omega f squared. So minus, so 6,400 then. Okay. So minus 0.96, so now we just have to add pi to it, so the equations work. So 2.18. Good. Now if you want to see what these angles are, of course that's easy to check. So this one multiple 180 divided by pi. Yeah, so 125 degrees about. Okay, anyway, so that's for it for question 2. Right, so exercise 3. We have a periodic external force that is acting on a 6 kilogram mass attached to a spring with a certain spring constant. We're told that the damping force is proportional to the instantaneous velocity of the mass, and it's 8 newtons when the velocity is 2. Okay, and then find the frequency at which resonance occurs. Okay, so this is a very quick question. So 3. All right, so all that second part about the damping tells us is that this is there's a proper damping force with a damping constant as we used it in our modeling, which in this case looks to be 40 newtons per meter per second. So otherwise we're not going to use that information. All that we have to know is that the resonance should occur. For us, we understand that as when the angular frequency of the applied force is the same as the natural frequency. So in other words, all that we've got to figure out is what is the natural angular frequency. Let's write it just down so it's nice and easy question answer to read. So resonance occurs at or close to the natural angular frequency. And that simply, we use omega for that, so, and that is simply square root of k over m in this case. Okay, and we've got all that we need there. So that is square root of 150 divided by 6.0. So let's see, can we calculate what this is? How many times does 6 go into 150? Well, it goes 20 times into 120, and then 30 is left, so then this 6 goes 5 times into that, so this is 25. So 6 times 25 is 150. So this, yeah, okay, it works out nicely. Okay, so this is 5.0 radians per second. Okay, are we done? Well, look at how the question asks. It doesn't ask for the angular frequency, it asks for the frequency at which the resonance occurs. So this is not a frequency, this is angular frequency. So we want the frequency, and that is 2 pi over this. So it is 2 pi, 2 over 5 pi, and we can calculate that. 2 divided by 5, well. So 1 point, that's right, that's 1.3. So 1.3 hertz. Now to conclude with, let's consider some energy relationships. Specifically, let's consider the following. We know that the system keeps on oscillating in the long term, according to that steady state solution that we derived, that xp. And we know that it's going to have a fixed amplitude and a fixed frequency that's going to correspond to the frequency of the external harmonic force. So the system keeps oscillating, that external harmonic force is still there, supplying the system with energy, which is then dissipated by the damping force. Otherwise, there's this endless accumulation of energy, which we know that won't happen. So what we'd like to do now is to get an idea of what those values are. So let's see if we can derive an expression for the power being supplied by this external harmonic force, which is therefore also being dissipated. We know that the instantaneous power is given by this expression, because we know that this is the force, and then we know that this is the velocity, so the product will give us the instantaneous power from first here. So let's see this as this is the instantaneous power. Let's see if we can calculate what the average power is over one let's rather say over one cycle of that external harmonic force, one push and pull cycle. What is the average power being supplied to this system over one period of that harmonic force? And we'll do this in an exercise. Okay, so exercise 4, we've got to calculate the average power and show that it is of that form. Right. Okay, so let's write down what we know is the instantaneous power, so the previous expression. So we know that the instantaneous power is in watts, therefore is the speed at any point times the periodic force, so omega f t. Okay, so all this many watts, right? And we know that x of t, I mean, we're going to consider when we're past the point where the transient solution has any effect, so which we know will happen sooner or later, in most cases soon. And so then the solution of the system, now it's behaving, is that particular solution, the steady state, which we know is of this form, a cosine omega f t minus theta. And this, of course, we can differentiate to find x, and that's minus omega f a sine omega f t minus theta. All right, so I can find an expression for this. So p is therefore equal to minus omega f a f0 cosine omega f t times sine of omega f t minus theta. Right. Okay. So what is it that I actually want to calculate? I want to calculate the average power over one cycle of this harmonic force, so that I can see what that is. I'd like to plot it and investigate and see what it behaves like. Well, we're expecting it's similar to it will have a similar resonant effect, that's a suspicion, so we want to check that. So we need an expression to play with, to look at. And so what we're going to calculate for average power is, in other words, this expression. The total energy transferred or dissipated is P dt from 0 to t, where t is one period, one cycle of the force. So this many joules, then 1 over t to get the average power in watts. Good, so this is what I want to calculate. So I want to be able to integrate this thing. This is just the definition. So I want to integrate this. And okay, so that means I'm going to have to simplify this a little bit. So let's simplify it until it's in a form in which we think that we can go ahead and integrate it. Okay, so once again, we're going to rely on those addition formulas for the trig functions, in this case sine. So minus, let's see, what do we have here? Omega A, cosine omega ft, and then this is sine omega ft, cosine theta, sine minus cosine omega ft, sine theta. Okay, and the minus, I can means those to flip around. Let's absorb the minus and multiply in this. So then we're left with omega fa f0. So if the order switches, if I've taken the minus, so then the cosine, so I'm left with cosine squared omega ft sine theta minus this term, so minus cosine omega ft sine omega ft cosine theta. Okay, good. And this I can simplify. So here you should be able to recognize some of these terms that you were told, probably told how to deal with in first year calculus modules. So the tricks you use for square roots of trig functions like this. If you want to remember the formula, I'm never quite sure, but I know where it comes from. I know if you have cosine 2x, and that is cosine squared x minus sine squared x. And I want the expression for cosine squared, so I'm going to use, let me just quickly go through it. Cosine squared x minus, and then this is 1 minus cosine squared x, because cos squared plus sine squared is 1. So therefore, cos squared of x, if I take it to the side, then this side will be 2 cosine squared of x. So there will be 2 here, and then minus 1. So it will be cosine 2x plus 1, but half. Yeah, half cosine 2x plus 1. That's how I remember it. So this will become half cosine 2x plus 1 times sine of, oh, not x, t sine theta. All right, good, excellent. So that expression I can integrate. Okay, so that's very good. Minus and that term I remember. That is just this whole story, sine of 2x is equal to 2 sine x cosine x. So this is minus a half sine of twice omega ft, and then the cosine theta tags along. Good. All right, excellent. That we can actually integrate. So let's integrate it. Find the definite integral. So this is then equal. So what I want is 1 over t integral from 0 to t p dt. And that is therefore, all right. I can take out half as a common factor. So I am left here with omega fa f0 over 2t times the integral from 0 to t. Sure. Okay, let's see. I'm left here. I'm going to multiply this out. So that is sine theta plus cosine. Yo, pay attention, pay attention. First x, and then I made a t, and that wasn't right either. This is cosine squared. The angle is omega ft. So this should be, this here should be 2 omega ft. Okay. All right, well, I don't like doing this, but let's use Tipex, and it'll be dry in short order. Let's just remember, remind me to get back to it. So that should be 2 omega ft. Okay, so cosine of, what do we have here? 2 omega ft sine theta. I took it off, okay, minus sine 2 omega ft cosine theta and dt of the whole story. Good. All right. Now, The definite integral of this is, of course, by basic definite integral properties is the same as the integral of to 0 to t of this plus the integral from 0 to t of this minus this. Now I'm going to leave it to you to figure out or realize rather that the integral from 0 to t of this expression is just 0 for a very obvious reason, because this I'll leave to you to think about, because t is the period of that function. This integral from 0 to t of this expression works out to be 0. Okay, so all that we're left with essentially is then just this, the integral from 0 to t of sine of theta. And what is that? That is just t sine theta, because remember sine of theta is a constant now because we're differentiating with respect to t. So all that we're left with here is a half omega f a f0 sine theta. That's it. And now we have an expression for a, that tremendous large expression, so let's use it. So let's put everything else to the side. So omega f f0 over 2 times a. Okay, so that's that massive expression. So that is f0 over square root of, okay, this entire thing, omega fb squared. Now I can already see what's going to happen, because I'm going to have to square it again. Well, I added minus k. This is the other way around, okay, but that doesn't matter. A minus b squared is the same as b minus a squared, no matter. Multiplied by sine of theta. And now go look in the previous lecture and in the lecture notes how we wrote the expression for a the first time. It is why writing sine of theta as a y value over a radius term. You can't remember, we had tan of theta equal to this omega fb over that term. I can't remember if it was the other way around. I think it was the other way around. K minus omega f. Yeah, it was like this, I believe. Yes, it was like this. Good, we had like this. Now if you interpret that as a y over a x term, then sine of theta is therefore equal to omega fb over the same square root. Omega fb squared plus m omega f squared minus k squared. Good, and then these two are simplified, so we are left with b omega f, and then that force amplitude is squared. Well, I see the expression asks us to take the m out, but okay, that's just taking an m out, and that this bottom square root simplifies. I'll leave that to you. That is simple enough to do. Let's just write this as omega fb squared plus omega f squared minus k squared. Good. Okay, and then you can take out m from the out of space. You can take out the m common factor, and then you get exactly that expression that the question asks for. Okay, so all of those calculus techniques do still play a role. Oh yeah, we shouldn't forget, what should this have been? 2 omega f. Okay, 2 omega f d. Right, that's better. Okay, so all those calculus techniques and stuff play a role, and we have been able to now find a nice expression for the average power, which we can now go ahead and investigate and plot it and see what it looks like. Okay. And now finally, let's see if we can observe the same resonance effect for the average power of the external force. And indeed we do, at least in the cases where the system is capable of oscillating by itself, which is the top two cases, b equal to 15, b equal to 200. You know from third chapter work how to tell if the system without the external force will correspond to overdamped or underdamped or critically damped, and for those two values of B it is underdamped, so it is a system that is capable of oscillating by itself. And if the external force then is being applied at the frequency that corresponds to the natural frequency of those oscillations, yeah, then you have this resonance effect. But in the case where the damping is too strong and the system is not capable of oscillating by itself, there is no resonance effect. Okay, and that is it for Chapter 4, Forced Harmonic Motion.